right, so here we have a sled. We're pulling on it, and we know that we're doing work on it, and since there's friction, we can assume that friction is doing work on it as well. So what we'll find is that whatever our kinetic energy at the end is going to be less than the work that we did. That means that's because the work done by friction is negative, right? Okay, so it decreases the energy, the final energy of the sled. And there are other forces acting on the sled as well. Weight is acting straight down. Normal force is acting straight up. How come we're not worried about the work done by them? They're perpendicular, so they don't do any work, right? All right, so if we draw, we can, since friction is part of this, I do want to include normal force, include all the dimensions here. So we have our applied force, we have normal force, we have mg acting downward, and we have frictional force acting this way. Kinetic or static? Kinetic friction, right, because it's moving, okay? So the total work done on the sled is going to be equal to its change in kinetic energy, all right? But we also know that the total work done on the sled is equal to the work done by our applied force plus the work done by the frictional force, big F, little f, okay? Something that Dr. Seuss spoke. Now, what we could also do is recognize that the total work done is equal to the work done by the net force. So we can add those together, but we're actually solving for friction, so since we don't know that, we should keep them separate. This is one of those circumstances. Remember I told you before, two ways you can find the total work. One is to say the sum of the work done by the individual forces, or we could say the work done by the net force. Okay? You should get the same answer. You will. But in this case, we don't know one of them, and it's actually what we're solving for. So this way right here is the more appropriate way. Okay? So we're going to take these two things and put them together, and we're going to say that the change in kinetic energy is equal to the work done by the applied force minus the work done by friction. Okay? So let's start with friction. Why do we know that it's negative? We know that the work done by friction is going to be equal to the force of friction times the distance that we're traveling, right? So this is kinetic friction, right? That's going to be equal to mu times, okay, cosine theta, thank you. That is important, okay? So we have mu kinetic times the normal force, right? I'm just going to write it as normal force to start with. I think I made it capital up there, but you get the difference. D cosine theta. Okay? That's a pretty extensive expression there. All right, so we got mu, and because looking right here at our forces acting in the vertical direction, we're not moving in the vertical direction, we're not accelerating in the vertical direction, we're on a level surface, so we know that the normal force is equal to mg. All right, so coming down here, we're going to say mu kinetic times mg times the distance times the cosine of the angle between them. All right, let's take a look at the angle between them. We know that the displacement is in this direction. We'll call that the positive direction. And we know that the friction is acting in this direction. The angle between them, 180 degrees, or pi if you're a math head. That means that cosine theta here, cosine of 180, is going to be -1. Okay? Negative work. That means that our total expression here is going to be negative mu k mg d. All right? That's our expression for what? Work done by friction. Okay, so we're going to plug that in up here. All right, so now coming down here, we're just going to take these two things and put them together. We're going to say delta Ke, change in kinetic energy, is equal to the work done by the applied force, which is just going to be Fd, right? And we're going to assume they're in the same direction. I don't know if it says they're parallel. So the force is 24 newtons times 8 meters, right? So we got 24 newtons times 8 meters. You know what? I've got it algebraic. Let's keep it algebraic. We've got Fd, and then cosine theta is just going to be 1 minus mu k mgd. Craziness. All right. So now, what about Ke? Delta Ke. Okay. Well, yeah. Let's take a look at it though, since we know that's Ke final minus Ke initial. All right. It starts from rest. All right. So we can leave that out. That's equal to Fd minus mu k mgd. All right. So this is 1/2 mv squared, v final, right? is equal to FD minus mu K mgd. Now I got to do a bunch of stuff because what are we trying to solve for? Let's not lose sight of that. Wait, what's the question again? We're trying to solve for mu K, right? All right, so now we just have to do some algebra voodoo, rearrange stuff. I'm going to move this over to this side so it gets positive. Mu K is equal to, this stayed on the same side, FD minus 1/2 mv squared over mgd, okay? So now, what we could do is, we could do some algebra and reduce that or, change it and simplify it. If we were in math class, I would suggest we did that, but I don't think we need to worry about it. So mu K, you know what we need to do here? I'm going to give you a hint. I'm going to do it in green. Yes, dimensional analysis, because what do we know about mu? It's supposed to be what? Dimensionless, right. All right, so FD we know is work, right? So that's joules, minus 1/2 mv squared, that's kinetic energy, that's joules. And mgd, same form, same dimensions as mgh, which we know is potential energy, so that's energy. So joules minus joules over joules is equal to 1, right? It's dimensionless. All right, so we know our expression is at least probably set up correctly. It's dimensional, right? It's not 0. It's not j. J minus j is equal to j when we talk about it dimensionally, right? All right. So group those, make it a little smaller. Right, that's our dimensional analysis. So FD, what's our force? It was 24 newtons, right? Times distance, 8 meters, minus 1/2. What was our mass? 16 kilograms. V final was what? 2 meters per second, right? 2 meters per second squared. I know that I am not putting my correct sig figs in there. Mass, again, 16 kilograms times G, 9.8 meters per second squared, times the distance, again, is 8 meters. So here we got some, need the calculator crew here. Mu K is equal to, drum roll please. All right, so calculator crew says 0.13. And what are the units again? None. It's dimensionless. We have a coefficient of kinetic friction.